Welcome students of Standard 12. The aim of this upload is to give a detailed summary of each chapter just before the board exam of the 12th, whichever set is going to appear for the board exam. Having gone through the exercise of the whole year's portion, going through the lessons from the teachers and from their own reading, at the end of the year, before the examination, before the board examination, it would be nice for the students to have a picturesque view of the entire concepts learned. With that idea, I am starting with electrostatics. Now, the first chapter that we have got in our book is electrostatics. In this particular session, we are going to deal with electric fields, forces, effects on charges due to electric fields, and the vector notation of electric fields and the forces, the accelerations that are producible on the test charges, and the effects due to the accelerations, Gauss's theorem, concept of flux. If time permits, we will go on to the application of concept Gauss's theorem, but else we will stop with this in the first session. Then we also have mentioned about electric lines of force and properties and quantitative study of the electric lines of force. Now, taking our first thing, the Coulomb's law. What does Coulomb's law say? According to Coulomb's law, the force between two charges Q and Q2 kept in air or vacuum is given by FEA. A stands for air and E stands for electric field, equal to Ka into Q1 Q2 by R square, where Ka is also written as 1 by 4 pi epsilon naught Q1 Q2 by R square. Here Q1 and Q2 are the two charges, R is the distance between their centers, Ka is the electrostatic constant of the medium containing Q1 and Q2, in this case air or vacuum, and epsilon naught is the electric permittivity, which you see on the second part of the equation, is the electric permittivity of medium, here air, and so epsilon naught. Now, force between Q and Q2, if considered in medium other than air, will be Fe and M standing for the medium, will be Km into Q1 Q2 by R squared, which is equal to 1 by 4 pi epsilon M into Q1 Q2 by R squared, where FEA and FEM is the force between the same pair of charges with the same separation considered in air first and then in medium respectively. Now, the vector notation of the forces is represented in terms of which we consider which one we consider as our victim charge, and which we consider a source charge. So, for example, if Q1 is the source charge and Q2 is the victim charge, F21 represents the force on Q2 due to Q1. And also remember, like charges repel and unlike charges attract. So, force on Q2 due to Q1 is repulsive along the line joining Q1 to Q2, that is, along the position vector of 2 with respect to 1, if Q1 and Q2 are like. So, and F21 is along Q2 to Q1 if Q1 and Q2 are unlike. In both cases, we are only seeing the charge on 2 due to 1. So, if both 2 and 1 are like, it will be radially outward along Q2 to Q1, along Q1 to Q2 if both of them are like, and along Q2 to Q1 towards the Q1 if both of them are unlike. If F21 is the force on Q2 due to 1. For Q1 and Q2 both being positive, F in air T1 will be equal to the force on 2 due to 1 will be 1 by 4 pi epsilon naught into Q1 Q2 by R squared into R of unit vector of 2 with respect to 1. Because 1 is the source charge, with respect to the position of the source charge, we have to see the position vector, and it will be along the position vector's direction, unit vector's direction. Where R cap is the unit vector of position vector of R21, which is Q of Q2 with respect to 1. Fe21 is the force on Q2 due to Q1. In the above equation, if Q2 and Q1 are both negative, then Q1, Q2 will be minus into minus, which will be still positive, and F21 remains parallel to R cap 21. If, however, Q1 is positive and Q2 is negative, or Q1 is negative and Q2 is positive, Q1, Q2 will be minus. So F21 will be anti-parallel to R of 2 with respect to 1 cap. Same way, if you are making Q1 as the victim charge and Q2 as the source charge, F12 force on 1 due to charge in air is given by F12 vector is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 the whole square, modulus of that, into R12 cap vector. When you take F12, you have to take care to see R12 cap, where R12 is the position vector of Q1 with respect to Q2, because Q2 is the source charge now, and R12 is the unit vector, R12 cap is the unit vector of position vector of Q1 with respect to Q2, which is acting as the source charge in this context. As explained before, for both Q1 and Q2 being positive, or both Q1 and Q2 being negative, F12 is parallel to R12, and F12 is along minus R12 if Q1 and Q2 are unlike. That is, Q1 is positive and Q2 is negative, or Q1 is negative and Q2 is positive. Note, in all our study of electric forces, we choose the test charge Qt to be so small as compared to Qs, the source charge, that the presence of Qt does not alter the already existing position of the source charge or S assembly of source charges. The main important thing that I would like to explain here is, if Q1 is going to be here and acting as the source charge, and if Q2 is going to be here acting as the test charge, the force exerted by Q1 on Q2 is equal and opposite to the force exerted by Q2 on Q1 according to Newton's third law. So, if Q1 exerts a certain force, the same is the strength of the force exerted by Q2 on Q1. Still, if Q1 is going to be very large, or in other words, its mass is going to be very large, that will cause a sizably small acceleration on Q1 and appreciable acceleration on Q2. So it's always better to have the test charge to be so small so that it is victimized for acceleration, and by bringing in the source test charge, the source charge is not either driven away or drawn towards, and its already existing position does not change. This is the meaning of telling this statement. We choose the test charge to be so small compared to the QS, to be so small compared to the source charge. That is the meaning of it is the presence of Qt should not alter or drive away or draw closer the existing position or the source charge that is already present. Electric field. Electric field is defined as the force on a unit positive test charge placed at the given point of choice due to the source charge or the charges around in the neighborhood. E is equal to limit of F by Qt on Qt tending to 0. Unit of E as referred to from RHS is Newton per Coulomb, because F stands for Newton and Qt stands for Coulomb. So this will be Newton per Coulomb will be the unit of E, where V is volt. It can also be later on told as V by meter, volt per meter, where V is volt. The definition of volt and other things will come in the next session. Now, vector notation of E due to Qs in air is equal to E in A on is equal to K Qs by R square. This with the derivation I am not doing because it's the end of the year and just the period before the public examination, where Qs is the source charge. Here test does not come into play. The test charge does not come into play. It is E as the point is only dependent on the medium of choice, the source charge, and as well as the distance of the given point from the source charge. It does not depend on what test charge you are imagining there. It should be a unit test charge. When I say unit test charge, it can be 1 Coulomb or 1 microcoulomb or 1 millicoulomb or 1 picocoulomb as the context may be. If Qs is of the order of Coulomb, perhaps 1 millicoulomb may be good enough for a unit test charge. If this is of the order of itself, by itself it is of the order of millicoulomb, then you have to choose a microcoulomb as a test charge. Only then it will be very small and its position will not alter the already existing position of Qs. If Qs is of the order of microcoulomb, we have to find out QT, which is of the order of picocoulomb, and so on. So QS is the source charge, R is the distance of P from the center of QS. Epsilon naught is the electric permittivity of air, because we are seeing only the electric field in air, and that is, R is the unit vector of point P, whichever point we are considering, or the location of the test 1 coulomb of test charge with respect to the center of this. From here, QS can be positive or negative, but the definition of E warrants that QT should be unit positive. Very important, it should be unit positive. If QS is positive, then EP is parallel to R cap, as I explained before. If QS is negative, the unit test charge will be drawn towards it, and therefore it will be anti-parallel to the position vector of that point P. Also, QT should be very much less than QS. That is, modulus of QT should be very much less than modulus of QS. If QS is of the order of Coulomb, QT should be of the order of millicoulomb or microcoulomb. Principle of superposition of fields due to many charges around a small test charge QT. Here, position vectors of Q1s, Q2s, Q3s, etc., Qns vary with respect to some common chosen origin. So, let position vector of Q1s from a common origin be R1 cap, and of Q2s from the same origin be R2 vector, and so on, and Qns be Rn. So, let Q2 be the position, be at position vector of R from the same point 2. Now, R of Qt with respect to 1 will be taken as follows. This is how we arrived at the result. Position vector of test charge with respect to Q1s. So, this is R1, that is the position of Q1 with respect to the common origin O, and this R is the position of the test charge with respect to the same origin O, and therefore this is R1. O to Q is R1, O to P, say O to Q is R, O to Q1 is R1. Therefore, position vector of Qt with respect to Q1 will be R vector minus R1 vector. Similarly, position vector of Qt with respect to second source charge Q2 will be R minus R2, and so on. And the position vector of Qt with respect to the same Qn will be R minus Rn. Now, E1 at P will be, due to the first charge Q1, what is the electric field at P? Will be 1 by 4 pi epsilon naught into Q1 by R1P, R of P the whole square, into unit vector of Rp with respect to 1, where E1 is the electric field at P due to Q1 alone. R of P with respect to 1 is the position vector of P with respect to Q1 alone, and R by R of P with respect to 1 cap is the unit vector of the position vector of P with respect to Q1 alone. E1 is positive or negative depending upon Q1 being positive or negative respectively. Similarly, R of P with respect to 1 is R minus, putting R of P with respect to 1 as R minus R1 as I earlier explained. Now, E1P will be equal to 1 by 4 pi epsilon naught Q1 by R minus R1, the R vector minus R1 vector, the modulus of that difference vector, the whole square, into R of P with respect to 1, the cap. Similarly, E2P will be 1 by 4 pi epsilon naught into QP by R vector minus R2 vector the whole squared into R of P with respect to 2 the whole cap, and so on. And ENP will be 1 by 4 pi epsilon naught into Qn by R vector minus Rn vector the whole square into R of P with respect to n the cap. Thus, now all these are vectors. This is to remind that R of P with respect to n is not the same direction as R of P with respect to n minus 1, and so on. So they are all vectors, and this is unit vector in that direction. So E vector will be E1 vector plus E2 vector, etc., some of which may be positive or negative as the case may be. RH is a vector addition, E1 vector, E2, etc. Each E1 vector can have its own x, y and z components in the 3-dimensional space, and E resultant will also have x, y, z components as explained on vectors. E resultant on E resultant's x component will be E1x vector plus E2's x component, etc., En's x component. E resultant y will be E1's y plus E2's y plus, etc., En's y. and E resultant Z will be E1Z, etc., etc. Note that all E1x, E2x, E3x, etc. will be either along the x direction or negative x direction. It can either, that means this coefficient can be either positive or negative. So an algebraic addition of all these will give me the x component of the resultant. Similarly for the y and similarly for the z. And E total can be found using the vector notation of E total will be Ex square plus Ey square plus Ez square, as for any kind of vector study. Next, note, though it remains that there are electric forces on Q1, Q2, Q3, etc. due to the rest of the charges in the neighborhood, these mutual forces existing between the different sources themselves does not alter the field already existing at P on the 1 Coulomb of test charge. The point is, see, we know there are so many test charges, source charges. So Q1 may exert a force on Q2. There may be a force between Q1 and Q2. There may be a force between Q2 and Q3, and so on. So each of the source charges is a victim to the force due to the other charges in the neighborhood, but those will not affect the individual forces that they exert on the test charge. That means each one will exert a force given by its own characteristic magnitude and its own direction, as if the other charges were absent. This is one thing that students should not realize. So that does not alter the field at P on the 1 Coulomb of Qt due to Q1, Q2, etc. When we focus on force on unit positive charge at P, we consider only Q2 as equal to plus 1 Coulomb at P to be the victim, and simply consider the forces due to Q1, Q2, Q3, etc. Qn individually on this Qt of 1 Coulomb, and need not take into account the forces on Q1, etc., etc. due to the rest of the charges in the assembly. In other words, each of the source charges Q1, Q2, Q3, etc. exerts its own field at P as if other charges were absent. The presence or absence of any other charges does not alter the electric field at P due to the individual charges. However, the resultant field at P is a function of the presence of other charges and the location of each, since EP is the resultant of all the individual fields. This is one important thing. In problems involving force or field at a point, the location of source charges may at specific geometric specific geometric locations as vertices of an equilateral triangle, or vertices of a square, or vertices of a rectangle, or vertices of a hexagon, etc. In such cases, the geometry of the figure will help us to find the distance of and direction of the P with respect to Q1, Q2, etc., etc. Also, if the structure is a two-dimensional structure as a circle, square, rectangle, triangle, etc., E resultant will be having no third component in the third dimension, that is Ez can be taken as 0, if the vertices are locations of some charges are in the xy plane. Unit of E resultant is Newton per Coulomb or volt per meter, as explained before. The direction of E resultant should be determined and noted down in the answer presented in the paper. Say along PK, where K is the point on the resultant. Force suitably should be marked. Also, force on any Qt at P will be equal to L. Supposing I am placing a test charge. That test charge that I am that is suggested in a problem may be positive or negative. Only when you define E, it is necessary that Q2 has to be positive, and you derive your direction on the assumption that Qt is positive. On the other hand, if you are going to place any other charge Qt, then you can have Qt as equal to, it's not necessary Qt has to be 1 Coulomb, it's not necessary Qt has to be necessarily positive. Anyway, having been given the direction of EQT, you can find out the force on Qt, the new test charge that you are bringing, by using the equation. The F on Qt is EP into Qt. F on Qt is EP into vector EP into Qt, and this F will be parallel to EP if Qt is positive, and F will be anti-parallel to EP if Qt is negative. F on Qt equal to now what is the now you know F is equal to ma. That holds good even for electrostatic forces. So force on Qt equal to mass of Qt into Q of Qt, where m is the mass of the test charge and Qt is the acceleration produced on the test charge, as per Newton's second law applicable to all kinds of forces. So don't think electrostatic force will behave in a different way, different from what Newton has just told about force. Whatever be the force, F is equal to ma. Now, therefore, in any given problem, if you are given the mass of the test charge, you can easily find out what acceleration it will be subjected to and what distance it will travel in a given time, what will be the path it takes, whether it will take a circular path or a straight line path or whatever it is, based on whatever we have studied as displacement in the 11th standard class. Now coming to relative permittivity or dielectric constant of a medium, we're going to tell you how the permittivity of the given medium, electric permittivity of the given medium compares with the permittivity of air or vacuum. Now the dielectric constant epsilon r is given by epsilon m by epsilon naught, where epsilon m is the electric permittivity of medium and epsilon naught is the electric permittivity of air. So numerator will be permittivity of medium, denominator is epsilon naught. You should remember that. Definition of epsilon r in terms of forces between two charges. So you have got the fundamental definition is epsilon r is epsilon m by epsilon naught. But you have got other definitions also which you have to make a note of, so that will come in handy when you are solving the problem. Definition of epsilon r in terms of forces between two charges. For two charges Q1 and Q2 separated by a distance r, if Fa is the force in air and Fm is the force in the medium, and for the same pair of charges Q1 and Q2 and same separation r, Fa will be equal to 1 by 4 pi epsilon naught into Q1 Q2 by r squared, modulus of the force. Modulus of the force in the medium for the same two charges being present in the medium will be 1 by 4 pi epsilon m into Q1 Q2 by r squared. These both will remain the same in both the equations. So if you divide 1 by 2 Fa by Fm, you will get this will cancel, this will cancel, 4 pi will cancel, so this epsilon m will be pushed to the numerator, so it will be epsilon m by epsilon naught, which is epsilon r. Thus you can think of dielectric constant of a medium as the ratio of force in air to force in medium between the same pair of charges held at the same separation. This may come in handy even for your entrance exams of IIT and all that, where they may just give you the definition and ask you to identify which of the different clauses given the four options is epsilon r. Now definition of epsilon r in terms of electric field at P. You know, electric field is different from electric forces between two charges. Whenever I say electric field, I am making one of the two charges, namely the test charge, as unit positive. In terms of now electric field at A is equal to 1 by 4 pi epsilon naught into Qs by r square. Electric field in medium at the same point at the same position r, it will be 1 by 4 pi epsilon m into Qs by r square. Qs I am not changing for the same with respect to the same Qs. Therefore Ea by Em will be again, it will be epsilon m by epsilon naught, which will be epsilon r. Thus dielectric constant of a medium can also be thought of as ratio of electric field at a point in air to electric field at the same point in the medium due to the same Qs at the same location in both cases. Right. Now units of Km, epsilon m and epsilon r. Km is the electrostatic constant given by this equation as already explained. Unit of now this unit of Km will be cross multiplying, it will be unit of Fm into unit of r squared divided by unit of charge the whole square. So that will be a unit of force is Newton meter square per Coulomb square. So this will be the unit of electrostatic constant. Okay. Newton per this will be the unit of electrostatic constant. Newton per meter square per Coulomb square. Since Km is nothing but 1 by 4 pi epsilon m and unit of epsilon m is reciprocal of unit of Km because 4 pi has no unit. Therefore the unit of epsilon m will be reciprocal of unit of Km. Therefore unit of epsilon m will be, instead of Newton I will have Newton power minus 1. Instead of meter square, I will have meter power minus 2. Instead of Coulomb square, Coulomb power minus 2, I will have Coulomb square. So the unit of epsilon m will be Newton power minus 1, meter power minus 2 and Coulomb square. Since epsilon r is epsilon m by epsilon naught, both epsilon m and epsilon have the same units. So the epsilon r is a mere ratio and it has no units. Next, it has been found that Ka for air, electrostatic constant, has been found to be 9 into 10 power 9 Newton meter square per Coulomb square. So if you calculate epsilon naught in terms of this Ka, epsilon naught will be 1 by 4 pi into Ka, which will be 1 by 4 pi into 9 into 10 power 9. If you calculate this, you will get it as 8.85 into 10 power minus 12 Newton power minus 1 meter power minus 2 Coulomb square. Epsilon m is found using the data for epsilon r. So if I know epsilon r as to be 80 for a given medium, and epsilon m naught is 8 point this thing, so epsilon m will be epsilon naught into epsilon r, which will be 8.85 into 10 power minus 12 into 80 times 80. And so many, that answer will be the absolute electric permittivity of the medium. Sometimes epsilon r is also written as K in some of the problems or the question paper or while you are teaching in the classroom. So that K is also the dielectric constant. If it is electrostatic constant, they may write it as some Ka or something like that. So it's for the students to distinguish in the context of whatever comes in the paper or in the class board or wherever, the what that K refers to. It can sometimes refer to electrostatic constant depending upon its position in the numerator or denominator, right? And therefore, electric lines of force. Properties of lines of force. Students would have already learned since the revision series comes at the end of the year just before board exams. Important points. Lines diverge out of positive charge or charges and converge towards the negative charge or charges. Tangent drawn to the line or line of force at any point gives the direction of the electric field at that point. The lines are crowded in strong field region and are far apart in the weaker field region. Okay. Lines are parallel in a region of uniform electric field. Now what is the meaning of electric flux associated with the surface? Here the area vector is somewhat catchy, so I would like to illuminate the students on that. Now area vector for a vector is a vector. Area we know is a scalar, but in certain cases area is given a vector like treatment. So area is taken as vector, which is modulus of S into n cap. Here what is the meaning of that n cap? This only bears the vector characteristic of the area vector, where n cap is the unit vector of vector representing the outward drawn normal to the surface. S is the magnitude of area. The line segment drawn as outward normal to the given surface should have suitable length marked on it so as to represent the area of the surface according to a chosen and defined scale. For example, if the area of the planar surface A dash B C D is going to be 6 meters squared, we can draw a line OX which is perpendicular to the entire flat surface of A dash B dash. OX represents the outward normal drawn to the surface A dash B dash C D, the front surface of A dash B dash I am talking about. On this, OX, on this OX you mark OL to represent the area. The scale can be say 1 centimeter equal to 1 meter squared. So for an area of 7 meters squared, OL should be 7 centimeters. So OL vector will represent the area vector of the entire surface above chosen. And defined scale, if n cap is the unit vector of OL of OX and OL is the by 7 meters squared, OL will be equal to modulus of this OL in times n cap, where n cap is 7 meters squared, and because 1 centimeter is 7 meters squared. So n cap is 1 meter squared along OX. Having defined the area vector, we know electric flux associated with the surface is given by integral of E dot ds is going to be your flux associated with that surface. The surface can be open or it can be closed. Now it is E modulus of E into modulus of ds vector E dot ds. It will be modulus of E vector, modulus of ds vector, that is area vector, into cos theta will be my phi electric, or more specifically d phi electric, small elementary electric flux associated with an elementary area E, right? Now where E is the electric field associated with the given position of the area, and ds is the modulus of the area vector of the surface, and theta is the angle between ds vector and E vector. Understood? Both of them diverging or both of them converging. It follows that E vector is perpendicular to ds vector of the surface. Angle theta between E and ds is 0 and cos theta will be 1. So flux associated will be is maximum and positive because cos 0 is 1. If the electric field lines are tangential to the surface, that means if supposing you have if the electric field is going to be, this is the surface A dash B C D, and if the electric field lines are going to be in this direction, tangential to the surface, the outward drawn normal OX is perpendicular. So cos 90 is 0. So therefore, the electric flux associated with the surface will be 0 if the electric field lines are parallel to or tangential to the surface. This is one thing students may get confused when they are applying this for the sheet of paper or a line of charge and so on and in problems. Note, for E tangential to the surface, ds is perpendicular to the surface and phi is 0. Students should exercise caution in understanding the wordings given in the problems describing the E with respect to the actual given surface or the area vector of the surface. If they tell you the angle between E and area vector itself is something, straight away you can use the cos of that. If they say the angle between E and the surface is that, you have to take the complementary angle. If the surface is closed as the closed surface of a cube and a charge is enclosed inside, one has to consider the surface area of all the six faces that the cube contains. Similarly, if it is going to be a sphere, it should be a lateral surface area 4 pi r squared for the sphere. If it is going to be a cone, it will be pi rl plus pi r squared at the bottom. Like that, they have to brush their mensuration and take the proper area. Take into account certain areas and discard the other areas depending upon the angle between E and ds for that surface. If E is a function of ds, also you cannot pull out E out of the integral. If E is told as a function of the area that you are going to consider for the given surface, then you have to take it inside and write it at what suitable function of ds as given in the problem, and you cannot take it out. If by symmetry E is a constant, the value modulus of E is a constant, direction alone changes, then mod of E can be taken out, and if theta between E and ds remains 0 for all points, as in the case of spherical surface with a charge at its center. Okay. Now, a modulus of E at P equal to see here the modulus of electric field at P is equal to magnetic field at L, because all of them are equidistant from the center, namely the radius of the sphere, and therefore EL and ds, angle between EL vector and ds vector at this particular point is 0, and EL vector and ds vector at this point also is 0, and therefore, right, electric field and similarly here it is the same, and therefore it is 0 at all points, and so on for all. So phi will be equal to integral of E dot ds. So you can take the modulus out and into cos 0, into cos of 0, which is cos 0 is 1. So E into that can be taken out, and therefore E will be integral of ds. So if it is for a sphere, you take it as 4 pi r squared, where r is the radius of the sphere, and E will be equal to phi by supposing in a problem you are given E and you are also given phi. How are you going to find out what is the surface area, or how are you going to find out E? If this is given and this is my question mark, E is my question mark, how are you going to find out? E will be equal to phi divided by S. They may give informations about phi and S, and they may ask you what is the, they may also ask you about what is E, yes, and then and say that theta equal to 0. Supposing they say theta equal to 0 in this case alone. Otherwise you have to write S cos theta. E will be equal to, more specifically speaking, it will be phi divided by S cos theta. Yes, S cos theta, where S is the area that is studied, and the integral of ds cos theta, right? S cos theta. Unit of phi will be Newton per Coulomb into meter squared. Even if cos theta is going to come there, it has no unit, so it will be Newton meter squared per Coulomb. Phi is also, instead of Newton per Coulomb, I can write it as volt per meter, and volt per meter into meter squared, it will be voltmeter. Voltmeter is different from the voltmeter that you are measuring. The measuring voltmeter is meter, This is volt meter. This is one unit and this is another unit. Remember that. Gauss's theorem. Integral of d phi equal to q by epsilon naught, where q is the charge enclosed inside a Gaussian surface and q is the enclosed and where q is the charge enclosed inside the Gaussian surface and q is the charge inside the enclosure. That, in other words, that is enclosed Gaussian surface. That is, q is the charge inside the enclosure. If the surface and the charge are considered, if both the surface as well as the charge enclosed are considered in a medium other than air, it will be, if it is air, according to Gauss's theorem, this will be equal to phi by epsilon naught, where epsilon naught is the permittivity of air and the charge and the surface are considered in air. If for the same medium, it will be integral of d phi inside the medium will be total flux associated with the closed surface will be equal to q, same q in the center by epsilon m, where epsilon m is the permittivity of the given medium. Students can appreciate that unit of RHS is unit of q by unit of epsilon m. So it will be Coulomb, and epsilon m is Newton power minus 1, Coulomb square and meter power minus 2. So it will be Newton can be pushed out, Coulomb square will cancel. So it will be Newton per Coulomb into meter square, Newton meter square per Coulomb, which is earlier discussed and same again is same as what was discussed, same as what it should be, should have as unit. Phi electric should have as unit. So phi into unit, and therefore E into S, which is phi into for electric field into S, which is same as the quantity on the right hand side. Also note the following points while solving problems. Q total, the total charge enclosed is the algebraic sum of the charges enclosed with the plus and minus signs. That is what you should know. If there are more than one charges, you just have to take the algebraic sum of all the charges. Some of them may be positive, some of them may be negative, and you have to add them with the positive and negative and with proper units for. If one of them is taken as microcoulomb, the others also should be converted from whatever unit they are specified in the problem to the suitable microcoulomb units. If sigma of Qi is equal to 0, supposing there are Q1 is equal to plus 3 microcoulomb, Q2 equal to minus 3 microcoulomb, Q3 is equal to 5 microcoulomb, Q4 is equal to minus 2 microcoulomb, and Q5 is equal to minus 3 microcoulomb. If you add all the positives together, it comes 3 plus 5, which is 8. And this becomes also, minus also becomes minus 3, minus 2, minus 3, which will be 8. And therefore, this is minus, this is minus, and this is minus. All the three negatives added together gives you 8, and all the positives added together gives you 8. Therefore, the sigma of all this becomes 0, and that in that case, the total flux will be 0. Also, the total flux does not depend on the location of the individual charges with respect to the inner wall of the surface considered. And epsilon r is equal to the total flux in the air by flux in medium. That will also, that gives you the third definition. We saw it in terms of electrostatic force. We saw it in terms of the electric fields at the same point and the same source charge. And we are now finding out what is we are comparing the ratio of the electric flux in air to flux in medium due to the same charges enclosing a closed surface, first in air and then in, and that ratio is also epsilon r. Okay. While integral of d phi of air is flux associated in surface in air, and integral of d phi in medium is the flux associated in the medium. If the charges are not discrete but continuously distributed over the whole body, we call it as continuous charge distribution. If they don't have fixed charges in different locations, there are three types of continuous charges distribution. For the body being a linear structure, as a wire or a rod charge, the charge is uniformly distributed along the length of the charge. That is called the linear density of charge. And for Q is the linear density, and L is the length of the entire structure. the total charge on the linear structure is Q and L is that. So Q by L. Unit of lambda will be Coulomb per meter. If the structure is a thin sheet, like surface as shown here, you find that with thickness being negligible and area being pronounced, then the surface density of charge is called into play. That will be the charge divided by area, where A is the area of the surface, and unit will be Coulomb per meter square. If the body is a three-dimensional structure with all the three dimensions equally significant, like a solid cube or a solid sphere or a solid cylinder or a cone or whatever it is, the volume density is Q divided by volume. Unit of rho will be equal to Coulomb per meter cube. Application of Gauss's theorem and electric dipoles and theories associated with electric dipoles will be discussed in brief and summary written in the next session. Thank you.